Let's say we have a positive charge, capital Q. This will be our source charge. Now, if we bring another charge which is also positive, let's call it small q, this will be our test charge. We know that due to the presence of capital Q, which is also positive, the small q charge, which is our test charge, will experience an electrostatic force, F, which will accelerate it away from the positive charge capital Q. What if we want a quantity that is independent of our test charge and depends solely on our source charge and the distance between these two charges? For now, let us call it R. Then the electric field vector, which is represented by E, capital E exactly does that. Electric field vector is equal to force per unit charge. In this case, it will be our test charge, which will be equal to K Q small q over R square divided by small q. Then it will be equal to K times the source charge divided by the distance between R square and the point where we previously had a test charge. So notice that we have gotten rid of our test charge small q. The electric field only depends on the distance between the source charge and the point where we want to calculate our electric field. Now let us write this equation in a better form. Let's draw our axes. This will be x-axis and this will be our y-axis. Now let us call this a source charge capital Q and this as the point P. Let R dash be the position vector of a source charge and R be the position vector of the point where we want to calculate the electric field. Then the distance between them will be equal to R minus R dash vector. We can now write the electric field as K times our source charge divided by magnitude of R vector minus R dash vector multiplied by R cap, where R cap is a unit vector along the line joining Q and the point P. So this will be our R cap. So this is our final definition of the electric field. Now what if we have more than one source charge? Let's say we have Q1, Q2, Q3 like this up to Qn, and we want to calculate the electric field at this point P. Now we can define the distance between P and Q1 as R1, similarly between P and Q2 as R2 and P and Qn as Rn. Now we know that since the electrostatic force obeys the principle of superposition, then the electric field must also obey the principle of superposition. So the net electric field at the point P will be equal to the electric field due to Q1 alone plus the electric field due to Q2 alone, like this, till the electric field due to the charge Qn. We can write this equation in a compact form. Electric field at the point P is equal to K, which is a constant of proportionality, times the summation. I goes from 1 to small n, Q sub I divided by R sub I the whole square. This is the definition of electric field when we have more than one point charges. we need to add the unit vector r cap also. Now, what if instead of discrete point charges, we have a continuous source of charge? In that case, the electric field becomes an integral here of dq over r square times r cap. Now let us take a look at continuous line charge like this, and we want to calculate an electric field at the point P. Then we can consider a small length element dl. Let's say this line charge has a charge per unit length of lambda. Then lambda will be equal to dq upon dl. Then we can write dq as lambda dl. So we can substitute lambda dl in the place of dq in our equation. Then we will get the electric field due to a continuous line source of charge as k line integral of lambda dl over r square r cap. Here r is the distance between the source charge dq and the point P. It will be a vector equation. Similarly, if the charge is distributed over a surface, let's take any surface, and we want to calculate the electric field at the point P, then we simply take a small area element dA and let the distance between this area element and the point P be r, and let the charge per unit area with sigma be equal to our charge dq over our area element dA. Then we can simply separate dq as sigma dA. Then the electric field due to a continuous surface charge distribution becomes constant of proportionality k times the integral of sigma dA over magnitude of r the whole square times r cap. Here it will be an surface integral, so let us write S to remind us that it is an surface integral. Now let's take a look at our last case. What if we have some volume in which the charge is distributed and we want to calculate the electric field at some point P due to this charge distribution? Then let us take a small volume element in the shape of a cube. Let us call it d tau, and the distance between this volume element and point P be r. Now let us define rho, which is charge per unit volume, as volume element dq over d tau. Then we can separate dq as rho d tau. Then the electric field in the case of continuous volume distribution becomes constant of proportionality k times the integral rho d tau over magnitude of vector r squared r cap. This will be a volume integral, so let us write v to remind us that it is a volume integral. So this whole will be the electric field due to continuous volume distribution.